So we understand that in the transmission line, on the surface of the transmission line, corona happens, and we are interested in corona happening in transmission lines. There are other regions where PD happens. We're not going to discuss that now. Now, if you look at the different modes of corona, depending on the polarity of the high voltage electrode and depending on the magnitude of the applied voltage and therefore the electric stress at the surface of the conductor, you would have different kinds of corona happening on the surface of the conductor. So there are various modes of the conductor depending on the polarity as well as the magnitude. So this picture does not depict a particular AC full cycle. This shows you when you have positive polarity. This shows you when you have negative polarity. By positive polarity, I mean that the conductor, the high voltage conductor, is positive with respect to ground. By negative polarity, I mean that the high voltage conductor is negative with respect to ground. And these show the various magnitudes. So if you look at the positive part only for the moment, so what I'm trying to say is that when your conductor is positively charged with respect to ground, and you apply a voltage for a certain range of voltages, as long as the field at the conductor surface is lower than the corona inception field, there will be no corona. You cross that and then you will see onset streamers. What are onset streamers? Onset streamers are essentially some transient discharges that you will see on the surface of the conductor. They are not stable, but they have the function of distributing. So there is some ionization going on, and that ionization is not enough to establish a stable glow, but there are streamers, there are transient discharges, and these transient discharges are kind of distributing conducting particles in the gaseous medium around the conductor. If you go further than this range, then you see a steady positive glow. So the region, a local region around the conductor will have ionized, and you will see a steady bluish white glow. And this is what you have most likely seen. If any of you have seen a corona happening on the surface of a transmission line, what you would have seen is, you would have seen that there is the conductor, and around the conductor you would have seen a stable bluish white glow. So that is what you see the positive glow. Now, if you increase the voltage further, what you see is, again, there is the stable glow, and over and above the stable glow, from the glow, emanating from that stable glow, you will see some transient discharges. So essentially what is happening is, there are some discharges, very similar to what we discussed in the streamer mechanism. There are some discharges which are causing ionization of the air further and further away from the conductor surface, and these streamers are redistributing charge in a bigger region around the conductor surface. And obviously, if you increase the voltage further, breakdown happens. And when I say breakdown happens, this is to be distinguished from corona or partial discharge. Breakdown happens means there is a continuous conducting path between the high voltage and the low voltage conductor. That means now there is a line to ground fault. So as I said, you start with corona, and there may be corona and you don't really have a major problem, except of course for some losses, because corona means you have conducting particles, you have charged particles moving around. Charged particles moving around means you have current has I square R losses. So if you have corona, you have heating, you have losses, but the medium continues to be insulating. However, if you keep on increasing the voltage, this can lead to breakdown, total breakdown, and you can have a major problem in your hands. But of course, before positive glow goes on to breakdown, there will be some more pre-breakdown streamers, which will give you a kind of warning. What are the different corona modes that are possible when the high voltage conductor is negative with respect to ground? It is quite similar, but there are some important differences. Of course, as long as you are below the corona inception field, there is no corona, even if it is negatively charged. Then, as you cross that if you cross that critical field, instead of seeing onset streamers, you will see trickle pulses. What are trickle pulses? Firstly, They are not streamer discharges. Streamer discharges may be transient, but they're not quite pulsative in nature. They are of more longer duration. Trickle pulses are pulsative in nature. So you will see that on the conductor surfaces, there are some red. Trickle pulses are red in color, which is very different from the color in case of a positive discharge, positive corona. So that is how you can distinguish between just by looking at it, you can distinguish between positive corona and negative corona. There is a color difference initially. At the initial stage. And then, so what you see is on the surface of the negatively charged electrode, before you see any corona, you will see some red pulses coming and going. Now, when you increase the voltage further, you will see a steady glow, just as you see in case of the positive case, you will see a steady negative glow. Increase the voltage further and you will see pre-breakdown streamers, again very similar, and then you increase the voltage further and you have breakdown. So the modes are very similar in case of positive polarity as well as negative polarity, except for, of course, these onset streamers in case of positive polarity and trickle pulses in case of negative polarity. There is one more difference which may not be that obvious, and that is if you take a comparative look at the positive cycle and the negative cycle, you see there is a difference in the magnitudes. In the positive polarity, breakdown will take place at a lower voltage or lower field, and you will need much higher fields or much higher voltage to be applied on a negatively charged polarity, negatively charged electrode for breakdown to happen. And this is because there is a difference in the manner in which corona proceeds to break down for positive polarity and corona proceeds to break down in negative polarity. Let us see a little more about these differences between positive polarity and negative polarity. So the main difference is, of course, trickle pulses. And why do you have trickle pulses when you have a negative corona? Look at this particular electrode. The needle electrode is negatively charged and this is your positive electrode. So when you apply an electric field, you have ionization in the region which is right next to the tip of the electrode. And ionization means you have positive charges as well as electrons. Now this is further from the positive electrode and very close to the negative electrode. The electrons have to travel a large distance to reach the positive electrode. And they move fast. The positive electrons are massive. They will move slowly, but they have to move very small distances because the ionization happens very close to the high voltage electrode. So this is what you see when you have an avalanche in progress. And when this is happening, what you can see is you will see a reddish spot glowing along the length of the wire. So even though I show it for the negative electrode because I'm trying to simulate the non-uniformity factor, this negative electrode could be an irregularity on the surface of the electrode. So wherever you have an irregularity, you have a local field intensification, you will see a reddish spot glowing along the length of the wire. Then what happens is, as the avalanche continues to progress, more and more negative ions and electrons are moving towards a positive electrode. Some of them have been sucked in, and there is a cloud of negative electrons here, and there is a bigger cloud of positive electrons in front of the negative needle or the negative irregularity. So in this situation, what you have is you have a kind of charge separation. So you have a region of positive charges and you have an extended region of negative charges. And therefore, there is an effective charge separation and there is an induced electric field, or rather a space charge electric field, which is pointing from the charge center of this positive ions to the charge center of this negative ions. So you have now a space charge field ES. Initially, you had only E naught. Now you have ES superimposed on E naught. So therefore, the field that you see here is a reduced field E naught minus ES, because ES and E naught are in opposite directions, and E naught minus ES may become less than the critical field required to sustain the corona. And at that point, the avalanche stops. And the trickle pulse is eliminated. It is extinguished.